Yeah, thank you very much, Peter, for the, as always, kind introduction. And I'm very happy to see so many participants here. And let's see how deep we can dive into this aspects we just touched on the surface. So functional split option for centralized RAN, basically meaning we want to adapt the functional split maybe to the backhaul requirements. This is an overview of my talk, and you see here. So the first question: why do we need a flexible RAN split at all? I mean, everybody works quite fine now, right? So maybe we should change anything. But the answer is, of course, yes, we need to do something. And then we talk about the different functional split option itself, about decision factors, about the RAN bandwidth and latency requirements which we experience, about the functional placement, so where can we put some radio resource management function, what basically does it then cause, and also something a little bit about architecture implementation aspects. Okay, so you saw this slide here already, but maybe you will see some more often. It all comes back to this. There's a trend of cloudification which comes from the IT realm, so to say, goes into the communication networks industry, and this is unstoppable, so to say. So it goes also together with commoditization of hardware, and then you gain also flexibility, meaning that you basically can decide where to put certain functions, radio resource management function, RAN functions. You can decide to put it close to the base station. You could decide to put it somewhere in the cloud RAN. The question is when and where do you do that? So this purpose, we have this concept of flexible functional split, meaning again, just for reiteration, on the right-hand side you have the full CRAN implementation with baseband pooling, where only the radio part here is decentralized. All of the rest is basically in a central entity, and here is the other extreme. This would be basically somehow the current distributed LTE network. And then we have to find the right split. For example, if we have a good backhaul, we split here somewhere on phi. If you have not such a good backhaul, or maybe there are some other aspects which we need to decide here, then we make a split somehow, or we centralize some radio resource management functions in order to get some gain. Maybe important to say here is that there's a difference, of course, between virtualization and centralization. If you just virtualize a radio base station, it doesn't mean that you have a centralized or coordinated radio resource management. Yeah? These are two different things. If we speak about centralization, we always mean that we have a coordinated effort for interference mitigation or for joint processing and so on. So we have different functional split decision factors. This is somehow kind of a high-level overview. What we think here, first of all, we have centralization gains. So if we, for example, centralize scheduling, then of course we can do inter-E or inter-cell interference mitigation by deciding when to schedule a certain UE, when to schedule a user in one cell versus when to schedule another user in another cell. And this centralization gains, as we will see later, these partially depend on where we put this functional split. Then we have the backhaul on radio access network constraints. So as you all know, there are different kind of backhauls which all have different capabilities. The questions which we had to face in our project were, what exactly are these constraints? What are the capabilities? And there was some nice effort driven by Telecom Italia, which basically gave a comprehensive overview of different backhaul technologies, which we then could use for the mapping of functional split to backhaul technologies. Then we also think it's an operator optimization target. Maybe some operators, they want spend not so much money basically on a centralized deployment, or they want to reuse the existing infrastructure, then this has of course an impact on where to put this functional split. Maybe other operators want to emphasize certain aspects like OPEX, and maybe you would like to increase the energy efficiency of your system. Then this would mean that you have some kind of technology enablers which require then a certain functional split. This also needs to be considered. And of course, most important always are the costs and the efforts. So does it really make sense cost-wise to put a certain functional split in comparison to the revenue which you get them? These are the challenges which we are looking at. First of all, we need to find out what are the RAN bandwidth and latency requirements. So I'm more talking from the MAC radio resource management perspective, also trying to a little bit to get into PHY layer requirements, but we have a corresponding talk given by Dirk later, where he gives some more details on PHY aspects here. Together with radio access constraints, meaning basically what are some implementational constraints, where are basically some aspects in the LTE UU protocol stack which makes it better to avoid a split at a certain point. Then, as I said, centralization gains, can we really expect? Then we want to have a mapping to the different backhaul technologies, and then maybe we can identify a set of preferred splits. So let's have a look first at the LTE RAN protocol stack. I'm sure most of you are familiar with that, but nevertheless, we go a little bit here. To start here from the top, we have the radio resource control C-plane aspect, so basically doing connection control, connection management, bearer setup, all that stuff. Then we have PDCP, the packet data convergence protocol, which basically does security aspects, ciphering, but nothing which is related really to radio resource management. Then we have radio link control. Here, an important aspect is that we have the radio bearer buffers here. So the queues in the base station, they are located here on this radio link control layer. And this is some aspect which also need to be considered. Then we have medium access control. Here multiplexing takes part, and also hybrid IRQ, so fast retransmissions, so that we can basically flat out the effects of fast fading. Then we have upper PHY, what we call upper PHY here, including forward error correction. This basically takes part. Most of the computational effort is consumed by this forward error correction, at least in the uplink. We'll later see some very nice results on that from Peter. Then we have a lower PHY, which is basically everything, including detection, multi-user detection, and so on. Then we have the rest, analog digital conversion, pre-processing, RF processing, and so on. So if we look now on the bandwidth and latency demands, first of all, we look at a certain split here. Let's assume we have split D. So I start with from D to A, because I'm not so much a PHY guy. So we first look at split D. We look at split C here between MAC and PHY. This is basically the MAC-PHY split, also considered in femtoforum, for example. Then here's a split B, which means that the forward error correction is centralized, and then you have the split A. Now let's look at the bandwidth requirements. And we assume here this is a downlink system where if you have 20 megahertz, 2.2 MIMO. And we see here that we need here, for the bandwidth side, 1.8 gigabit per second. And on the latency requirements, we have 5 microseconds. This basically is a CPRI requirement. So it means that you have a very high requirement on the backhauls here. If we go one higher, then we already see here that we have already after analog digital conversion, we need here around 420 megabit per second and maybe around 1 millisecond latency. So this is still mainly driven by hybrid Q requirements, but also by channel state aging. So you need some kind of channel state information to a correct detection of the signal, and this must not be too old. So there we will have also more detailed explanation on this number later. Then if you go in the upper PHY, we have here already only the forward error correction, which is still left on the user data, so to say. So we have here an overhead added of maybe 1/3 on the user, or maybe half on the user data. So we have 100 megabit per second requirements. And we have 3 milliseconds latency requirements here. This comes from hybrid LQ. If we go now to Mac, even higher, then we see here that we only have the user data left, more or less. Of course, you have always some overhead due to packetization, maybe some signaling errors and so on. So you still have here some 70 megabit per second, still the same latency requirements. And if we go even further up in the split, then you see here starting here from the RLC, we get here the same 70 megabit per second. This is basically user plane data rate, but we can here say that we have very low or there's not so strong requirements on the latency, because the only thing which can be centralized really here is basically radio resource control, and we will see later that these are basically functions which need latency in around of 100 milliseconds and so on. So there are some more detailed results available, which is taken here from a paper submitted by Jens Bartel from Technical University of Dresden. And you see here that there's a detailed results available for these different splits in a variable case, or if we say we have a constant data rate here. So I hope that this will be available soon, and will also be available in the final deliverable. And what you also see here is the effect of multiplexing. So if you have several ISCs together, maybe 10, maybe 100 ISCs, so small cells basically together, and you consider a system where they are multiplexed, you see here that in the case of split A, you don't have any multiplexing gain, so you have one line basically, because everything is basically cell-specific data. And if you then consider different splits, you see here that with a dashed line that you get a good multiplexing gain that you can also exploit to decrease the cost. So what are these timing constraints? So this was basically bandwidth demands, so to say. We'll talk about a little bit about the timing constraints. One of the strongest is a hybrid LQ. You see it illustrated here in this figure. So on the left-hand side, they have here the UE, and you have here the framing, so in the uplink and the downlink. So we consider here basically the uplink. So the UE is sending an uplink message to the small cell here, and we assume here now that certain aspects, including hybrid LQ, are centralized here and the central entity called run as a service entity. And you see here that there is a requirement from CGP written in the standard that the ACNAC is expected in subframe n+4 when you have basically transmitted it. So basically it means that in the downlink the acknowledgement or negative acknowledgement must be received in subframe n+4. And then of course you have certain latency parts which add to the overall latency. We have here the air interface. Latency also has a certain latency, right? This is basically tackled by the timing advance, which is of course small in compared to the rest. Then we have here the backhaul latency. So this is basically illustrated here from the ISO to the run as a service. And then you have basically this much time left here in the run as a service, in the central entity, for the processing, for the decoding basically, and the frame building, and everything needs to then go back here, then in the end to the small cell, and then transmitted to the UE. So this basically means that in this scenario where we have maybe 700 microseconds delays or something like that on the backhaul, it leaves us around 1.5 milliseconds of time to do all the processing in the central entity. Not much. So there are other timing constraints. Now in this table you see here basically the different layers from phi to RRC, and what we did here, we looked at all the timers which are available or are considered in the CGP specifications. And you see here the timer, the purpose, and then you see the minimum value, the maximum value, and some default values. And there's a basic trend recognizable here. The higher you go here into the protocol stack, the less, the higher is basically the timing requirements. You see here that let's have an example here. RC connection reconfiguration has a timeout value of around 2 seconds. Of course, normally you would not use this high values. It just indicates that there's more loose requirements and that you don't need to stick to this very strong requirements of around 1 milliseconds and 4 milliseconds and so on. There are some other aspects which have been briefly discussed already. So if you look here on the protocol stack again, we have different kind of, let's say, granularities or handling granularities in the protocol stack. So up to medium access control, we have a per bearer handling of the data. So basically meaning that one UE can have different bearers and they can basically treat it independently from each other. As soon as we have been here in the medium access control, we have kind of per UE handling. So we have a multiplexing, which then is basically put together per UE more or less. And then you have basically after the forward error correction control, you have a per cell handling, which means then that on this split here, you have this transition between user-specific handling, and here you have cell-specific handling. This is something which can be also exploited for multiplexing gains. So I just show this overview slide again here. So we basically tackled bandwidth latency requirements and access constraints. So now we want to know what are the centralization gains which we can somehow expect from the different schemes. So there we have our protocol stack again. So what can be done at the different, let's say, layers of the protocol stack, right? The radio resource control here, there you can basically do something like load balancing, meaning that you can decide which UE is going to assign to which cell. This is basically the granularity where we can operate here. The other is handover schemes, so you can decide, do we do a handover or not, together with mission control. This is what we call connection control. If we go lower in the layer, we have here medium access control. Here's where already part of the scheduling is located, so we can do here some interference mitigation schemes. We can do some scheduling schemes where we decide to maybe to avoid some interference and so on. And if we can go even lower down here, then we can go into PHY, and here we have joint decoding schemes, we have cooperative multi-point processing schemes, we have in-network processing, and we have joint detection schemes. What is of course clear is that everything, so if we go down here in the protocol stack, everything which can be done here with, for example, split D, can also be done with lower splits. Yeah. So this is basically kind of, it can be added, so to say. The question is, can the gains from the different technologies be really added? And this is something which is still under investigation currently in the course of the project. So how does it look like if we identify these different basically function placement schemes? We identify 3. One is joint processing on PHY, one is centralized resource allocation. So this basically maybe requires something like 1 millisecond latencies or less even. Here we have maybe something around 3 milliseconds because of hybrid IRQ. And then we have centralized connection control where we say that this is in the area of 100 milliseconds. Okay, and another aspect here which I want to touch briefly is, if you talk about functional split, then one aspect is of course here what is executed in the small cells, what is executed in the RAN as a service. And this basically is the reason why we also develop cloud RAN architecture, so to say, or architecture for the cloud aspect of the RAN as a service. And you see here that we have here developed this virtual eNode B concept, and in this virtual eNode B, we have here the upper parts of the small cells, which together with the virtual parts executed here in the RAN as a service form basically or create a RAN functional split realization, meaning that one virtual eNode B can have, for example, split A, another virtual E can have split C, for example. Still, both virtual eNode Bs can interact together via the X2 interface, normal CGP interface, and you have a RAN as a service manager, and together with a virtual InnoB controller, which takes care that the constraints on processing and so on are really met. So, what are the centralization gains? Just some brief examples. So we talk here about centralized connection control, meaning that we have something like a split D, so centralized radio source, RRC, for example. And this is just two examples of the work package 3 candidate technologies, so CTs, which we consider. One is here on coordinated cell selection. This is basically this load balancing approach, which I have talked about. And you see here a really strong gain here from about 5 gigabit per second per square meter in non-coordinated case up to here around 7 gigabit per second per square kilometer just for this specific candidate technology. And another example here is energy efficiency. We can reduce increase the energy efficiency in terms of joule per bit here from 1 to 0.5 or even from 1.5 to 0.6. If we have not so many UEs in the macro cell. So this is for a cell DTX scheme where the cell is basically switched off at certain instances when there is no traffic available. Now if we look at another scheme here, this is the centralized resource allocation scheme, centralized scheduling. We have here something like cooperative radio resource management, where we do interference mitigation by means of our centralized solving of our interference graph problem. And you see here that here's the CDF of the area throughput again. If you look at the median and you compare to competing approaches, you have here also a strong increase from 1.5 to 2.5. And similar here for central coordinated scheduling, the different approach which takes into account the backhaul, the age of the backhaul, the age of the channel state information, given that you have some imperfect backhaul, and you see here compared here also to the baseline of round robin, you have a very strong increase with a max rate scheduler from 1.2 to above 1.8. So this is all work which has been done by my colleagues. So if you have some specific questions to these figures, I would reroute these questions to them. But what we have seen here is that there are significant centralization gains the lower you go into the protocol stack. The question is, how do they add up? This is, as I said, something which needs still to be assessed. Now we want to map these different splits to backhaul technologies. And as I promised before, first of all, we need to know what kind of backhaul technologies are available out there. Of course, always there comes some new ones, but there's a set of established backhaul technologies which we basically put together here in this table. So it goes from some XDSL-like technologies with very high latencies, well, not very high, but compared with the others, up to 35 milliseconds here, and low throughput, maybe 100 megabit per second, up to so-called dark fiber, where basically operator just use a dedicated fiber line here. Then you have 5 microsecond latencies, 10 gigabit per second, and so on. And we have here also considered all the wireless technologies, millimeter wave, microwave, license, sub-6 gigahertz unlicensed or licensed, also with different topology options, duplexing types, and multiplexing technologies if applicable. So, okay, how can it be mapped then to functional splits? You see it in this figure here. Maybe you see it more often today and tomorrow. And what we see here is on the x-axis basically the throughput of the bandwidth of the backhaul and the functional split requirements. And you see here on the y-axis the required latencies. And you see here that, for example, split A, so basically phi layer split, requires some fiber technologies, or passive optical networks will also be possible maybe. Split C then basically is all possible also with some sub-6 gigahertz technologies. And for XDSL options, only the split D is feasible at all. So we also managed to create this mapping. The question is now, what are the preferred splits? And unfortunately, I have to say there is no clear answer to this. As I said before, it will depend on the operator requirements. It depends basically on the scenario which you want to look at. And but what we did, we basically provided the tools to assess this identification of a preferred split given a certain scenario. So all this together, what you have seen before, led to this picture here, which is kind of high level, of course, but still there's within the project maybe somehow preference here for the split number B, because if you have this forward error correction centralized, you will see this very strong gains due to multiplexing gains, basically for computational complexity, which will be talked later about. So that's from my side. Conclusion, what to say? So the RAN flexible functional splits, I think, is some concept which enables operators to be flexible in terms of deployments, in terms of scenario, in terms of targets they want to optimize. And the challenge here is also to find the balance between centralization gains and costs. We tackled a lot of other challenges already, the latency requirements, constraints of the radio access, and so on. And in my opinion, RAN flexibility will be an integral aspect of 5G networks. We also see this in some of the projects which are proposed. And the question is, do we maybe need some relaxation of some certain constraints of the LTE RAN protocol stack? Will this be accepted by the industry in standardization bodies like CGP, which tend to be quite conservative, as we all know? So it will be an interesting time. And I don't know yet the answer to this. So, and thank you for your attention.
Perfectly in time.
Oh.
We kept the delay constant. Any questions from the audience? There.
Yeah, so when you talk about RAN flexibility, is it in terms of you expect to have one operator use one particular split for the deployment, or to perhaps mix the splits?
Yeah, maybe. Yeah.
And do you see any complexity in mixing splits, or with virtualization?
Yes, I think that's of course a question. How do you realize functional splits? This is why we basically developed this kind of concept here, that we have a virtual eNode B, and the virtual eNode B basically implements a certain RAN functional split. If you have, let's say you have a scenario where you have fiber, you can, in a stadium, for example, you can there deploy a set of virtual eNode B with functional split A. In the same, let's say, maybe not in the same, but theoretically in the same data center, in the same cloud environment, you can also have another virtual eNode B which implements another virtual functional split, which is basically here implemented with this kind of cloud RAN architecture. But there's a lot of, let's say, room for research and interesting developments still to do.
I have one question more for curiosity. If you do these different splits, your real-time capability might be different for your cloud RAN machine. Does that put any special requirements on the operating system you're using?
Yes.
Does that mean we have to think or rethink requirements for new or future operating systems? I'm asking the question because Google had this approach a couple of years ago where they tried to propose like an Android operating system for base stations.
Interesting.
Is that motivated from such things, or what can we expect?
To answer your first two questions, yes and yes. So I think it has very strong requirements on the operating system, and I guess that there is really some need to do some more work because the operating system, the OS people, the software people, so to say, maybe they don't know about these RAN requirements which we have. They don't know whether it's good or bad if maybe a frame is dropped. We say, of course, it's dropped. It's not good, right? They say for them maybe it's not so, not so terrible. So I think what our task from the communication people or from the communication side is to tell them what are the requirements, to make them understand these requirements, and then these kind of operating systems can be developed. Maybe they are already out there, I'm not completely sure about that, but I would expect that there are some kind of interaction, maybe interfaces even on, don't know, hypervisor side and the, some kind of RAN information could also be beneficial here. Regarding Google, Android, I don't know what the motivation was.
And does it pay off? Is the economy of scale, does it work on base stations? I mean, you centralize in less and less cloud RAN entities. Is that worth the effort? I mean, for operating system manufacturers, for maintenance and so on. Because
you mean from a cost?
Side, of course, scalability is there.
You mean from a cost perspective for, well, I mean...
Yeah, I mean, is someone doing this? I mean, are the Linux guys really
no, I don't think they do it now, and I think that the vendors, the RAN vendors should go there and really either push or make it on their own maybe even. From alone, I don't think that it will take it up.
So the infrastructure guys have to step in more or less to...
Either that.
Okay.
Yeah, but either that or a smart startup maybe comes and then everything can go very quickly, right?
All right. So thank you, Andreas.